Okay. All right, so we're recording now. So we're going to take a look at the pH of a buffer solution after we add a good bit of either acid or base. Okay. So if we take a look here at exercise 1613, okay, on page 571. And it says, suppose you add 50 milliliters of 0.1 molar sodium hydroxide to 1 liter of the solution described in exercise 1611. Now, 1611, we did that last class. And, okay, I don't remember off the top of my head, and I don't seem to have that one here. Amazingly. Huh. How do I not have that one? Almost every one of these problems worked. We did calculate the pH of the buffer solution in 1611 last class. Is that correct? Or maybe two classes? Yeah.
Yeah.
Does anybody remember what the pH was? Because that's actually one problem I don't have saved on my computer.
3.6.
3.6 it was? Okay. So let's remember that number. Okay. All right, so we're going to, in exercise 1613, we're going to add 50 milliliters of 0.1 molar sodium hydroxide to that solution, and we're going to recalculate the pH. Okay, so let's see, we had formic acid here. So let's get an equilibrium reaction up here for that. Sorry, my mind's kind of frazzled right now. So let's see here. Now, we're going to make an ice table here. Now, don't write these numbers in yet, right? So these were the numbers from the exercise 1611. So, but these are going to change. Right? Now, we're adding to this 50 mils of a 0.1 molar solution. Right? Now, when we add the hydroxide, right, that's a strong base. However much hydroxide we add, it will completely neutralize this. It will pull this acidic proton, here's the acidic proton, it will strip that off of the formic acid molecules. Right, converting the formic acid molecules into formate anions. Okay, this is the whole crux of the problem here. So I'm going to repeat that again. All right, when you add the strong base, okay, it will completely neutralize an equimolar amount of the weak acid. Right, it will completely neutralize it. So if I were to add, say, 0.05 moles, or sorry, 0.005 moles of hydroxide ion here. This would be 0.020, and this would be 0.023. Okay, because the addition of the strong base will convert the weak acid, it will pull off the proton, and the weak acid will be converted into its conjugate base. So we have to calculate the number of moles of hydroxide ion. We have to calculate the number of moles of hydroxide ion, right? So we had, and let's see, we had C1 equals, or sorry, we're going to use the molarity equation. Concentration equals moles over liters, right? And we're told that the volume is 0.05, volume equals 0.05 0.050 liter. And we're told that the concentration was 0.1 molar, I believe. Yes, 0.1 molar. And again, we don't write molar, we write moles per liter. So we can come back over here and check off what we know and what we don't know. I know concentration, I know liters, and I don't know moles. So let's rearrange that. We're going to have moles equals concentration times liters. All right, and we plug in here. So this is going to be 0.10 moles per liter. And the volume is 0.050 liters. All right, let me get, so I can cancel the liters here. And our answer here, let's see, we don't even need a calculator for this. Moles equals 0.0050 moles. Okay, so that's the number of moles of hydroxide. That's how many moles of this that we're going to lose, right? That's how many moles of this we're going to lose, and we're going to gain this many moles of formate anion. Okay? Everybody clear there? So we're going to put into this, so 0.0050. Now, we can erase this, and we can enter in here 0.020 moles. But we have a new volume now. The volume is not 1 liter anymore. All right, the volume is now 1.05 liters. And over here, we're gaining 0.0050 moles. So we're gonna, our total number of moles will be 0.023 moles. And again, the new volume is no longer 1 liter. Remember, the volume was 1 liter of the buffer solution, but when we're now adding 50 milliliters, so the volume has changed. All right. So there's our initial conditions. All right, so what's the change? Well, this will be minus X, this will be plus X, and this is going to be plus X. Okay? Now, let's go ahead and calculate when we do the equilibrium here. Let's go ahead and put those numbers in instead of rewriting this again. So 0.020 divided by 1.05 equals, and I get 0.019, 0.0190 minus X. This will be plus X, okay? And this will be 0.023 divided by 1.05 equals 0.0219 plus X. Everybody understand? If you got a question, speak up. Okay? If you got a question, speak up. All right, so now, sorry?
On Raymond, on this one, so for on this ice table, on the I, instead of putting that fraction in, can we put the equilibrium change right away or no?
You mean to put the 0190 up here?
Yeah, could we do that, or will
Sure,
it be wrong?
sure, you could do that. Sure, you could do
Okay.
that.
Okay.
Actually, we should understand here that these are this 0.0190 is a molar concentration, moles per liter here. Okay? Okay, I mean, sure, you could, yeah, you can put those up there. The reason I wrote them up here is so that you'll recognize that the volume has changed. That's why I initially wrote it like this.
Okay.
If I had the big board in the classroom, we would have calculated the concentrations off to the side. I just don't have room to do that right now. Okay? So now we can set up expression for Ka. So we'll leave that ice table up on the other one. Let's see. All right, so it's on the screen there. So Ka equals H3O plus times formate anion divided by the concentration of the free acid. All right, so from our ice table, we can plug in the values here. So this is going to be X, and the formate anion was 0.0219 plus X divided by the concentration of the, oh, sorry, this should be, yeah, okay, that's right. And this should be 0190 minus X. Let me just double check and make sure those are correct. Yeah, that looks good. Okay. Everybody see that? Okay, now we should do the Ca over Ka, right? The Ca over Ka, right? So we can do that right here. The Ka for formic acid, if I remember, is 1.7 times 10 to the negative fifth or 10 to the negative fourth.
Negative fifth.
Negative fifth. Okay. All right. So Ca over Ka equals 1.7 times 10 to the negative fifth, and this is 0.019. All right, that's going to be way bigger than 100. So let's calculate it out. 0.019 divided by 1.7 times 10 to the fifth negative. So that's over 1,000. 1118. All right, so we're justified in dropping the plus X and the minus X here. So let's go ahead and write Ka is approximately 0.0219X divided by 0.0190. Okay, so on the next line, we will solve this for X. So 0.0190 times X divided by 0.0219 times Ka, right? Times Ka is approximately X. Okay, everybody with us? So over here, I'm going to have to write really small here now. So we'll bring this up here. You should be going down your paper. All right, so we'll plug in the value for Ka. So X, hopefully you can see this in different colors here. Actually, I'm going to erase this up here. We don't need this up here. We only need the last line. All right, that way you won't get confused. We only need the last line. All right, so X is approximately 0. Oh, wait a second. This X should not be here. That should not be there. Please take that out. X is on the right-hand side. 0.0190 times Ka, which somebody just said is 1.7 times 10 to the negative fifth. Okay? Divided by 0.0219. And we get out our calculator. Let's see, and I did this problem before. We can double check. Somebody told me the wrong Ka. It's 10 to the negative fourth. 10 to the negative fourth. Okay, that would have still been bigger than 100 though. It would have been 118 rather than, or sorry, 112. Right, so we were still justified in that. It's 1.7 times 10 to the negative fifth, I think, for acetic acid. Okay, so let's go ahead and calculate this out. 0.019 times 1.7 times 10 to the fourth negative equals, divided by 0.0219 equals, and in scientific notation, I'm going to get, now we should only have 7 times 10 to the negative fourth. So that is X. Okay? But remember that X is the concentration of hydronium ion. X is the concentration of hydronium ion. Right? And we want the pH. So we can write H3O plus is approximately 1.47 times 10 to the negative fourth. Then that makes the pH is equal to negative log of H3O plus, which is negative log of 1.47 times 10 to the negative fourth, which is 3.83. Okay? Which is the answer in the back of our book. Right now, somebody had mentioned that when we did this without the addition of the hydroxide, okay, last class, which was exercise 3.11, the pH was 3.6, right? So it's only changed by 0.2 pH units. But remember, we added 0.1 molar sodium hydroxide, okay? Now, our book doesn't ask us to do this, but I'm going to do it just so you can see the effect of the buffer. We're going to calculate the pH of this solution if the buffer were not there. All right, but before we do that, do we have any questions? Let's just go back and summarize everything that we did. Okay, we set up the ice table here, right? We set up the ice table. Again, the whole key to this is recognizing that whatever amount of strong base you add, it's going to neutralize an equivalent amount of the weak acid, right? And when the weak acid gets neutralized, the weak acid molecules are converted into the conjugate base, all right? So converted into the conjugate base. So we have to recalculate the ice table, all right? So the concentration of the conjugate base will increase, the concentration of the original weak acid will decrease. From that point, it's just an ice table, right? And we should know how to do that from there. So the only thing different here was recognizing that the weak acid gets neutralized and converted into conjugate base. Let's see here. And I mean, again, from that point on, everything is the same. Don't forget, you have to take into account the dilution here, right? You have to take into account the dilution. So the volume is going to change by like 5%, okay? Sometimes, I think of one of the problems in the back of the chapter or the exercise, they actually tell us to ignore that, right? But the 3.83 we got is the exact same value in the back of the book. So at least for this problem, they did take it into account. Okay, any questions? Any questions? All right, actually, I'm going to leave these up here just for a moment. I don't need to erase these because we can calculate the pH of the solution without the buffer there on this small board. Now, we saw there was 0.0050 moles of sodium hydroxide, right? So we just calculated that. So let's calculate the molar concentration of the solution of the sodium hydroxide in the solution without the buffer there. Well, the moles equals 0.0050 moles. That's how much sodium hydroxide we have. And the volume is 1.050 liters. And we want the new concentration. The new concentration. So we have our equation. Concentration equals moles per liter. Right? So let's see. I know the moles, I know the liters, I don't know the concentration. So I can go ahead and plug the numbers in. Concentration equals 0.0050 moles divided by 1.050 liter. And we get out the calculator. 0.0050 divided by 1.05 equals, and I get 4.76 times 10 to the negative third molar. Okay? So that's the concentration of hydroxide, all right, with no buffer, okay? Now, we want to find the pH. Well, I know the concentration of hydroxide. I can calculate the pOH very easily, right? Let's see. I'm going to go back to this board here for that. Actually, I'm just going to do it on top of here. I don't think we need any of this. All we need is the concentration down there on the bottom. So again, this is the hydroxide ion concentration. Let's put that in. Hydroxide ion concentration. So pOH equals negative log of OH minus, which is equal to negative log of 4.76 times 10 to the negative third, which is 2.32. That's the pOH. All right, but we're after the pH, but we know pH plus pOH equals 14. All right, so hopefully you have this concentration written down on the bottom. So again, all we're doing is finding what the pH of the solution would have been without the presence of the buffer now. So pH plus pOH equals 14. So pH equals 14 minus pOH, or 14 minus 2.32. 11.68. 11.68. So that's 8 orders of magnitude. Remember, it was 3.83 with the buffer, 11.68 without the buffer. So that's 8 orders of magnitude, right? Remember, each difference of 1 pH unit is 1 power of 10 difference in the hydronium ion concentration. So 8 powers of 10, that's 100 million. Okay, so the difference in H3O in hydronium ion concentration with a buffer and without the buffer is a difference of 100 million times less with the presence of the buffer, or I should say greater with the presence of the buffer. It's 100 million times less without the buffer. Okay, so hopefully you're somewhat impressed by what a buffer solution can do for you. Okay, it really is an amazing solution. It really is. It's astounding what a buffer solution is able to do. All right, do we have any questions or comments? Because I think there is one problem for you to do. We're going to do just what I did here. Just what I did here. Okay. Let's see here. No questions. All right. Now, we have something called the Henderson-Hasselbalch equation, which is going to greatly simplify the calculation of the pH of. All right, everybody still there?
Yeah, we're still here.
All right, you know, it's amazing that when it comes back, it picks up right where it's left off and it's still recording. See, this Zoom is pretty good. I saw that Google tried to buy them.
No way.
The people at Google were using Zoom for their own video conferences rather than the Google software.
Wow.
The Google executives found that out. They tried to buy out Zoom and Zoom didn't want to sell. Okay, so let's take a look at Henderson-Hasselbalch equation. So let's take a look at, we have just a generic acid-base equilibrium equation. Okay, so we have that. Now, we can set up a Ka expression. Ka equals hydronium ion concentration times the conjugate base concentration divided by the free acid concentration. Oop, yeah, that was right, HA. Okay. Now, we can write this as, we're going to solve this equation for H3O plus. All right, so H3O plus equals Ka. We're going to move this over here and this down here times HA divided by the conjugate base concentration. I'm going to run out of room already. I can't believe it. All right, now let's just flip this around. Actually, I'm going to do that on the next point. We'll give you a chance to write this down. Although you're never going to have to derive it. Okay. Actually, I'm going to flip it around. We can squeeze that in on this board. All right, so there we go. Okay. Now, does everybody have this? I'm going to erase this line here. We'll keep the last line, get rid of this line. Okay, again, you're not going to have to be able to derive this, but I just want you to see where it comes from. There's a reason why you learn this logarithm stuff. We're going to take the log of both sides. Now, if you remember, the log of a product is equal to the sum of the logs. Again, the log of a product. I have Ka, right? So we can think of this as Ka times that. And we have a relationship from our, back if you think when you took algebra, the log of AB equals log A plus log B. Right, so we're going to use that now. Right, so this right-hand side can be reduced to log Ka plus log of HA over A minus. Okay, and again, this is still log H3O plus on the left-hand side. Okay, so I'm going to get rid of this here. We'll see, we don't need this. And so now I'm just going to multiply the whole equation by -1. Multiply the whole equation by -1. Negative log H3O plus equals negative log of Ka minus log of HA times or divided by A minus. Okay. Now, we'll give you a chance to finish writing that down. Again, there's a reason why you have to learn all that logarithm stuff in your algebra classes. At some point, it will eventually come in handy if you're a science major or engineering. Okay? Now, I'm going to rewrite this here. So I'm going to keep everything the same. Now in red here, we're going to use another little trick from our algebra class. So the log of x, the negative log of x over y, the negative log of x over y equals the log of y over x. What time is it here? It's getting close. Okay. Does anybody remember this relationship? The negative of a log equals the log of the reciprocal. Okay? So I can apply that here. Here I have a negative log x over y. All right, so I'm going to write that as log plus the log of A minus over HA. And again, you're not ever going to have to do this, but I just want you to see where it comes from. Okay, so can I erase this bottom line in red?
Yes.
All right, so there we are. We're almost there. We got one more step. Okay. Again, sorry about crowding everything together, but hopefully you've left space on your paper. Now, negative log H3O plus, that's just pH, right? That's just the pH. So I can write pH equals. Okay, well, negative log Ka, remember, the negative log of anything is just the P whatever. Like if this was negative log of OH minus, then we would call this the POH. Similarly, we can call negative log Ka pKa. pKa. Right, pKa. Right, and then we're going to keep this last term the same. Log of the conjugate base divided by the acid concentration. And there it is, the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation, right? So again, you can very quickly calculate the pH of a solution. All you got to do is know the pKa of, know the Ka of the weak acid, which you can look up in a table somewhere, okay? And know the concentration of the initial concentration of the conjugate base and the initial concentration of the free acid. So instead of having to make all that ice table and all that, you could just plug into this. I'm going to do an example problem here. We're going to calculate the pH of a buffer solution the old way and then this way. And we're going to see the difference here. We'll see the difference. All right. Any questions here? Again, you only need to know this last line in blue. I'm never going to ask you to do any of that other stuff. I want you to, hopefully you'll appreciate where this equation comes from by seeing it derived. Okay? All right, any questions or comments? So I'm going to do problem. If we look at the end of the chapter, problem 75, I'm going to do. All right, problem 75. All right. I should mention here, let's put the Henderson-Hasselbalch equation back up here for a second. And we should say a few things about it. Okay. Number one, it seems like biologists in particular, when they talk about weak acids or weak bases, they'll talk about the pKa, like amino acids are the 20 amino acids that make up proteins. They're all weak acids, right? So biologists won't talk about the Ka of those amino acids. They'll talk about the pKa values, right? The pKa values, right? And again, the pKa is essentially just the exponent. It's very close to the exponent on the acid dissociation constant. The other thing is, if your buffer utilizes a base and its conjugate acid, such as ammonia, right? You can still apply the Henderson-Hasselbalch equation. This NH4 plus is HA, right? And NH3 is the conjugate base. Okay, now you can find in a table Ka for this conjugate acid. But if you remember, we saw that Ka, earlier in this chapter, we saw that Ka times Kb equals Kw. So you can find in the table for ionization constants for weak bases, you can find Kb for ammonia. Then you can use this equation to find Ka for the conjugate acid. Right? So you can very quickly, using this equation, get the pKa for NH4 plus. Right? Very quickly. So even though this equation is written seemingly for weak acids, it can also be utilized for weak bases, okay? By recognizing that you can find the Ka for the conjugate acid of a weak base, right? Using this equation here, right? So we should recognize that. So again, two things. Chemists and but mainly biochemists and biologists will refer to pKa's of weak acids and bases rather than the Ka's. So if you take any of these biology classes, you should be aware of that. Okay. So we were going to do problem 75, which is a buffer is prepared by adding 39.8 mils of 0.75 molar sodium fluoride to 38.9 mils of 0.28 molar HF. We want the pH of the final solution. So we're going to do this the long way with the ice table, and then at the end, we'll redo it with the Henderson-Hasselbalch equation. So the first thing we have to do is calculate the number of moles of sodium fluoride and HF, because they're going to get mixed together, and we're going to have to recalculate the concentrations. So for NAF. All right, the molarity equals moles per liter. All right, and we want moles. So moles equals liters. All right, I'm going to skip lines of rearranging. I mean, you guys should know how to do that by now. Times molarity. All right, so I can plug in, and the liters are oh man. Oh, they changed the problem on me. All right, that's all right. We can still do it. The problem 75 in the old book that I have solved here is different than the one in our book. All right. That's all right. We can still do this. So 0.75, or sorry, the liters is 0.0398 liters times the molarity, which is 0.75 molar. 0.75, and again, I'm going to convert the molar to moles per liter so that we can cancel the liters here. All right, cancel the liters. We're left with 0.0398 times 0.75 equals 0.02985 moles. Okay, now we should calculate the new molarity here also, right? Calculate the new molarity. We know the moles, and the volume is just those two volumes added together. All right, so everybody understand what I'm doing here, right? Essentially, we're recalculating the molarity because the solution has been diluted. So concentration equals 0.02985 moles, and the new volume is here, actually, we'll write it out here formally. 0.0398 liter plus, what's the volume of the other solution? 389. All right, and that's equal to, so let's add these two together, 0.0398 plus 0.0389 equals, I'll put that into the second memory, so recall 1 divided by recall 2 equals 0.379 molar. All right, so that's the concentration of the sodium fluoride after it's been diluted. All right, after it's been diluted. All right, so hopefully somebody's going to write that down and remember it. All right, let's see a thumbs up whenever you have this all copied so we can do the HF after this one. Whenever you have it all copied, let's see a thumbs up. And I see 2 of them. All right, so now we're going to do the same thing for HF. All right, we'll switch boards. All right, so this is going to be for HF. All right, so let's see. Again, molarity equals moles per liter. We want to solve this for moles. So moles equals molarity, or constant, times liters. All right, equals. And the molarity of the hydrogen fluoride is 0.28 moles per liter. And the volume, I believe, is 0.0389 liters. Let me double check that. 0389. 0389. Yes, that is correct. All right, so the number of moles is 0.28 times 0.0389, and I get 0.010892 moles. I'm not worrying about significant digits at this point. So now we can calculate the new concentration. So the new concentration is equal to moles per liter, which is 0.010892 moles divided by those two volumes added together again. 0.0398 liters plus 0.0389 liters. All right, how come I don't have enough space here?
Raymond,
Yes,
is this also after dilution?
say again?
You had said that the sodium fluoride was after dilution for the concentration.
Right.
Is that the same case?
Yes,
For-
yes, that's what we're doing. Yeah, yes, we're doing the exact same thing, but for the hydrofluoric acid. You notice here the volume, this is the two volumes added together. So yes, this is after mixing them. You have to recalculate the concentrations. Okay?
Okay,
That's all we're doing right now is recalculating the concentrations because both solutions have been diluted. Each solution has been diluted by the other solution. Okay, does that make sense?
yes.
Okay, so I'm going to add these two together in the denominator. 0398 plus 0.0389 equals. Okay, so 0.10892 divided by recall 2 equals, that can't be right. 0.010892 divided by recall 2 equals. Okay, there, that makes more sense. And I'm getting, let's see, I'm going to write this in black. I don't know if you guys, can you guys actually see the different colors when I use the different colors up here? Hello?
Yeah, I can see.
Okay, because when I
Looks good.
looked on the YouTube videos for the high school class, the different colors didn't seem to stand out very much. 0.138 molar.
I wonder if I'm gonna have to use this as a.
Okay.
Ella. Oops.
Okay. Now, so now we have the two concentrations. So we can go ahead and set up our ice table. All right. So all that work was just to get the starting concentrations. That's all we've done. So we're going to write HF plus H2O gives us H3O plus fluoride anion, the conjugate base. All right, now we're going to make our little ice table with those new concentrations. All right, this of course will be 0. So let's see, This one is 0.138. And this one was 0.379. Someone check and please make sure I don't have those reversed. Actually, I know they're not. Yeah, that's good. This is going to be minus x, plus x, plus x. And then this will be 0.138 minus x. Same as always, we've been doing this a while. 0.379 plus x. Okay. Let me just check one thing here. That'll give you a chance to copy that down anyway. Okay. Now, we can set up our expression for Ka, and I think I'm going to go to the other board for that. I'll go to the other board. All right, we don't need this anymore. So let's take a look here. Ka equals concentration of hydronium ion times fluoride ion divided by hydrofluoric acid. Substitute in the values from our ice table, and we have x 0.379 plus x and 0.138 minus x. All right, so off to the side. Sorry? Sorry, I didn't hear you. All right, so we have to do our little test to see if we can drop these x's here. All right, so Ca divided by Ka, I'll go to the small board for that. Ca divided by Ka equals, well, Ca is 0.138 molar, and Ka for hydrofluoric acid is, got to go look back in the book. In section 1, hydrofluoric acid, 6.8 times 10 to the negative 4th. 6.8 times 10 to the negative 4th. That's going to be bigger than 100. All right, so recall 2 divided by 6.8 times 10 to the 4th negative, and it's 204. All right, so we can go ahead and drop those x's. All right, we can go ahead and drop those x's. Okay, we good here?
Yes.
All right, so I'm going to take this down. And we can write Ka is approximately x times 0.379 divided by 0.138. Okay, so we're going to solve this for x. X is approximately 0.138 times Ka divided by 0.379. Okay. And we'll bring this up here. Let's draw this line down. All right, separate it. So plug in the value for Ka. So x is approximately 0.138. And the value for Ka, as we just saw a moment ago, is 6.8 times 10 to the negative 4. All right, divided by 0.379. Again, 6.8 times 10 to the negative 4th. I know you probably can't see that. Then we get out our calculator. So recall 2 times 6.8 times 10 to the 4th negative divided by recall 1 equals. And I get 2.48 times 10 to the negative 4th. I hope this works out, because I didn't have this one worked out. I can't check it. All right, so that is the hydronium ion concentration. All right, so hydronium ion concentration equals, or is approximately 2.48 times 10 to the negative 4th. So that tells me that the pH equals negative log of 2.48 times 10 to the negative 4th, 3.61. Okay. Everybody good? Now, we're going to do the same calculation using the Henderson-Hasselbalch equation. Okay, same equation, or same problem, calculation using Henderson-Hasselbalch equation. Right, and for that, I'm going to bring back the big board here. We'll leave our ice table up here. Actually, I don't think we need it anymore. So it took us like 3 or 4 boards to do that. So we'll write down the Henderson-Hasselbalch equation here. So pH equals pKa plus log of the conjugate base divided by the conjugate acid concentration. All right? Well, let's see. Off to the side, I'm going to calculate the pKa. All right? So pKa equals negative log, and what was it, 6.8 times 10 to the negative 4th. All right, so 6.8 times 10 to the 4th negative log, so that's 3.17 after rounding. Right? So we can write back up here, actually, I'm going to skip some space here. We'll let you copy that down. Okay. So I'm going to switch to a different color for each line. So pH equals 3.17 plus the log of, let's see, the conjugate base concentration was 0.379, and hopefully I'm not getting these backwards. And this was, the free acid was 0.138. right? 0.138. All right, so now we get out our calculator. And I'm gonna calculate this term. So again, it's this divided by this, then your log key. All right, so recall 1. And again, someone please check and make sure I have those right. I'm almost certain they're correct though. Yes, they are. Divided by recall 2 equals log plus 3.17 equals 3.61. Isn't that what we had the first time? Yes, exact same answer. Exact same answer as we had before.
So Raymond, you just rounded it, right?
Yes, I did. Yes.
Okay.
All right. But if you remember, so here's the Henderson-Hasselbalch equation. Look how quick to get to 3.61. And we got 36.1 before, but look at all the stuff we had to do to get to the 3.61. So hopefully you understand how powerful the Henderson-Hasselbalch equation is. Plus, don't forget, we had to, this isn't even including the ice table, right? We skipped, I've already erased that. I just erased it off of the other board. So add the ice table on top of this, and all this work to get to the pH value versus Henderson-Hasselbalch equation, just this. You get the same answer. All right? So hopefully you have some appreciation for how tremendously simplifying a calculation the Henderson-Hasselbalch makes calculating the pH of a buffer solution. Okay? I want to mention a couple other things. Now, one thing that I don't want you to walk away from here without realizing, we did have to calculate, right? This 0.379 and 0.138, those are the diluted concentrations. So you remember, we began with 2 boards, right? One board was to calculate the diluted concentration of the sodium fluoride, and the second board was to calculate the diluted concentration of the hydrofluoric acid, right? So you would have had to do that for this Henderson-Hasselbalch equation. But we already had those diluted concentrations from the first problem, from when we did it, the first method. So this is method 2, and the ice table was method 1, all right? But we had already, so I don't want you to go away thinking, oh, it's only 3 steps. You still have to calculate these diluted concentrations, right? You still have to do that. You cannot just plug in the other, the starting concentrations that were in the problem, okay? So please, you might want to make a note of that in your notebook somewhere. What else? Now, let's take a look at the Henderson-Hasselbalch equation up here in black while we have it up here. Man, we only got one section in today, and we actually did half of this. We only did half a section. All right, but again, this is very useful. What we did today is very important, very, very important. We learned the Henderson-Hasselbalch equation, and we demonstrated the power of a buffer, that the pH changed very, very little by adding a big amount of hydroxide anion, right? And we saw that the difference between having the buffer and not having the buffer was a difference of 8 pH units. So hopefully you can appreciate the power of a buffer. Now, let's go back to the Henderson-Hasselbalch equation here, all right? Remember, a buffer is a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid. When does it work the best? Right? It works the best when the concentration of the conjugate base is equal to the concentration of the free acid. Right? I'm going to say that again. When the concentration of it, a buffer works best when the concentration of the conjugate base and the concentration of the free acid are the same. Because then this is 1, right? the log of 1 is 0. In that case, the pH is equal to the pKa of the weak acid. All right, this is very important, so I'm going to say it at least one more time. All right, here, let me get a pointer. All right. When the concentration of the conjugate base equals the concentration of the free acid, then this division here is equal to 1. It's equal to 1. The log of 1 is 0. So this term completely drops out. The pH is equal to the pKa of the weak acid. All right? That is the optimal condition for using a buffer system. That's when the buffer system works best, is when these two concentrations are the same. All right? Now, in practice, again, you can tweak this a little bit. Here, let's do this for, what was this? Hydrofluoric acid. So the pKa of hydrofluoric acid is 3.17. Actually, we have it right here, 3.17. I didn't have to calculate. But suppose you need a pH of 3.16, or sorry, 3.61. Well, you can tweak these concentrations a little bit and move the pH away from the pKa, right? So you might be doing some biological experiment where some biochemical reaction behaves optimally at pH 3.61, but your buffer is hydrofluoric acid. So the reaction might not occur at 3.17, but it occurs at a very good reaction rate of 3.61. So you can still use that same buffer system, but you can tweak the concentrations of the conjugate base and the free acid to get to your pH of 3.61. This buffer system will still work. It won't work as good as it does at 3.17, but you'll still get your biochemical reaction to occur. It might not occur at this pH, but it will occur at this pH. Right? So you can still get it to happen using the same buffer system. You just tweak the concentrations a little bit. Okay? So again, this buffer system is very, very powerful. Right? Almost every biochemical reaction is pH dependent. It only occurs within a narrow pH range, or at least optimally occurs within a narrow pH range. And then we saw the great power of the Henderson-Hasselbalch equation, right? The great power of the Henderson-Hasselbalch equation. Okay? Let's see here. Any questions or comments? Now, we only did a half a section today, but this was very, very important section. Very important. Now, in practice, if you ever have to calculate the pH of a buffer solution, you're going to use the Henderson-Hasselbalch equation. But you have to remember, you have to put the diluted concentrations in there. But in practice, when you're making a buffer solution, if you're working in a biology lab, I mean, any biology lab worth its salt, whatever the phrase is, will have some reference book where you can just look up and it will say, mix this many mils of the free acid solution, and this many mils of the conjugate base solution. You won't have to do this calculation. It'll be done for you in some reference book, but you should. So why do we do this in general chemistry? Because you should have some idea of where those things come from, right? You're just not, like reading a cookbook. You should have some feel for where these numbers come from. Let's see, what else did I want to say here? So we didn't get a chance to look at acid-base titration curves. We'll do that next class. Let's look at, on page 573, there's 2 concept check questions there. I want us to take a look at that and then we'll end. Okay? So we have, I'm going to write these down for considering that we're recording this. So concept check 16.5. And we have I hate when they write these acids like this. Actually, I'm not going to write it like that. This is acetic acid. And we want to know, well, let's finish writing this down first. All right. Okay, so let's take a look here. We have these 4 solutions, and to each of them, we're going to add 1.5 milliliters of 1 molar hydrochloric acid, right? 1.5 milliliters of 1 molar hydrochloric acid. So each of these solutions has their own respective pH, and the pH is going to change whenever we add the hydrochloric acid. And the question is, in which of these 4 solutions will the pH change by the smallest amount? Which of these 4 solutions will the pH change by the smallest amount? Now, does anybody have any idea? Anybody have any idea? And why? I mean, don't be afraid. It's not 4th grade. All right, nobody wants to take a guess, huh? Well, let's see. We just finished a section on buffers, right? So I would imagine, and we know that a buffer is a solution that can withstand additions of acid or base with resulting in just small changes in the pH of the buffer, right? So we should be looking for which of these solutions is a buffer. Which of these 4 solutions is a buffer? Well, clearly it's not this one. This is just a solution of a strong base. Clearly it's not this one. This is just a solution of a weak acid. Okay, now let's take a look here. Here we have 30 mils of hydroxide and 30 mils of, actually I didn't get the concentrations here. I believe they were both 0.1 molar. Yes, all right, 30 mils of 0.1 molar and 60 mils of 0.1 molar. Okay, now here I have 30 mils of strong base and 30 mils of weak acid, right? Now we should realize by now that the strong base will completely neutralize this. So we will know after we mix these, we won't have any molecules of acetic acid left. We'll only have acetate anions. We will only have acetate anions. So we'll, after we mix these two, 30 milliliters and 30 milliliters, we'll have 60 milliliters total. And the concentration of acetate anion will be half of this. So we'll have 60 mils of 0.05 molar acetate anion. So this will not work. This will not work. Now, let's take a look at this one. Okay? C and D are very similar, except the only difference is in the the volume of the acetic acid. Here I have 30 milliliters, which is completely neutralized by 30 milliliters of the base. Here I have 60 milliliters, only half of that is neutralized by 30 milliliters of the base. Only half of it is neutralized. So once I mix these two together, I'm still going to have some acetic acid left. but half of the acetic acid will have been neutralized by the base, turning it into acetate anion. So in D solution, I will still have acetic acid, but I will also have acetate anion. I will also have acetate anion. Okay? And if we wanted to, we could use the Henderson-Hasselbalch equation to quickly calculate the pH of this solution after we mix them together. Because again, the concentration of, we know that half of the amount of acetic acid is neutralized, turning it into acetate anion. So we will have equal concentrations of acetate and the same concentration of acetic acid. So that second term on the right-hand side of the Henderson-Hasselbalch equation is equal to 0. So the pH of this solution will just be equal to the pKa of acetic acid. So this is the one that will withstand the change of addition of the hydrochloric acid. But you see how you figure that out? You're looking for which one of these four solutions is a buffer. It's clearly not the first two. Here, again, hydroxide will neutralize the acetic acid. But unfortunately, since the volume and the concentrations are the same, it's going to neutralize every single molecule of acetic acid. Here, the volume of acetic acid is twice as much, so there will still be some acetic acid left. Right? So there's that answer. Any questions on that one? That was a good problem. I like that problem. This next question I don't like as much. Right now, unfortunately, I can't draw this up on the board, so we'll just have to say it. All right, and there's 3 parts to it. So they give us 3 beakers, and we're told that there's a weak acid, HA. So I see 4 molecules of HA and 3 molecules of the conjugate base, right? And they're asking on the right-hand side, which beaker on the right-hand side depicts the solution after addition of 2 formula units of sodium hydroxide? Well, remember what's going to happen there. The 2 formula units of sodium hydroxide will completely neutralize 2 molecules of the weak acid. So 2 molecules of the weak acid on the reactant side will be converted into A-, right? So we should expect to see, let's see, we started out on the left-hand side with 4 molecules of the acid and 3 anions. So on the right-hand side, we should expect to see 2 molecules of the acid and 5 anions. So that's Y. That's beaker Y. All right, answer is A. Okay, now the next question, any question on that? Again, you got to keep in mind here that when you add strong base, it will completely neutralize whatever acid is there. Completely neutralize it. That's what we just saw that here, and we just saw that in this second concept check, part A. Now in part B, we're asked, how many HCl molecules do we have to add and to reach the buffer capacity of this buffer system that's in the starting beaker? Right? Again, we should recognize that in the beaker on the reactant side on the left, that is a buffer system. We have some HA and molecules, and we have some anion. Okay, now they're not equal, the concentrations aren't equal, but it is a buffer system. Now, this is a term we haven't talked about yet, buffer capacity. What is buffer capacity, right? You have reached the buffer capacity when the solution can no longer withstand additions of acid or base with just resulting in just narrow pH changes. Here, let's turn back to 568 and look at figure 1611. Right, look at figure 1611. Okay, and we see there, so that orange box there on that pH curve. Right, that orange box is where the buffer is working optimally. You get outside that box, you've kind of reached the buffer capacity of this buffer system. If you start adding more hydroxide or more HCl, and you're reaching in regions out on the curve outside of that box, then the pH is going to start to change dramatically. Right? It's going to start to change dramatically. So back to this problem. All right, now, how many HCl molecules? Well, let's take a look here. So floating around in that solution, I have so the pink is the proton. So here's the acid molecule and here's the anion. The acid molecule and the anion. If I add HCl molecules, it's going to protonate the anions and convert them back into the free acids. Right now, the question is, remember, we have in the beaker on the left, we have 4 of these and 3 of these in the beaker on the left. So that's a buffer system. I have 4 acid molecules and 3 anions. Okay? So the pH is not equal to the pKa. There is going to be a little different. It would have to be the same for the pH to equal to pKa, according to the Henderson-Hasselbalch equation. Okay? Now, the question is, how many HCl molecules do we have to add until the buffer capacity is reached? Well, if I'm adding HCl molecules, I'm going to turn these into these. To have a buffer, I have to have some of both. So if I add the first HCl molecule, then I'm going to have 5 of these. Here, let's leave that up here. If I add the first HCl molecule, I'm going to have 5 of these and 2 of these, right? 5 of these and 2 of these. If I add the second HCl molecule, I'm going to have 6 of these and just 1 of these, right? 6 and 1. That's still a buffer system, but it's not working optimally. Remember, it works optimally when you have equal numbers of both, right? That's the optimal condition for the buffer system. So 6 and 1, I'm still buffering, but it's kind of weak. It's a very weak buffer system. So I would say I can only add 2 HCl molecules. Because if I add a third HCl molecule, I'm going to have 7 here and 0 here. That's not a buffer system anymore. 7 here and 0 here. That's not a buffer system anymore because I don't have any of the conjugate base left. Right? I've protonated all of it, converting it back into the free acid. However, if you look in the back of the book, the answer says you can add 3 molecules of HCl before you reach the buffer capacity. But I don't believe that. I think it's only 2, right? Because if you add that third one, you lose the conjugate base and you only have acid molecules left. Okay? Let's see. Part C says, draw a picture when the buffer capacity has been reached. So when the buffer capacity is reached is when all of these are gone. So you would just have 7 of these. You would just draw a beaker with 7 of these, right? Again, the buffer capacity has been reached when all of the conjugate base is gone, right? So if the answer is 7 base or 7 acid molecules, that means you've added 3 HCl molecules, you've reached the buffer capacity, exceeded the buffer capacity, I should say, which should say the answer to part B should just be 2 HCl molecules. Okay, any questions or comments? Oh man, I'm running late here. I've got to get rolling here. I'm going to stop recording here. I'm going to assign you some problems, and then I got to get rolling here. Let's see, stop recording.